Alright, hell yeah. So we got material mechanics and we want to make this problem real simple and solve it real fast. You know what I mean? I never do that. So we can make it simple just by making this bar just like that thing. You know what I mean? Just the smaller bar and throwing a P on it. And then the other thing that we can do is like, hey, grab the big bar and then throw that same P on it. You know what I mean? And this one, like I said, there's two ways to get to the answer. One is strength, is force over area. And then the other equation is kind of stretch, is change in length over length. This, they don't give you a strain. This is called strain, this is called stress. They don't give you any values for strain, and they don't give you any values for modulus of elasticity to say that, hey, strength is modulus of elasticity times strain. You know what I mean? This is a constant. You know what I mean? So it's like saying, hey, force is proportional to stretch. You know what I mean? Strength is proportional to stretch. Anyway, so at the end of the day, what we want to do is just be like, well, we know the area of the small bar. We're going to say that's area 1 and area 2. These are circular, and they're given the diameter. So, and we're saying a max strength. I like to say strength. It just makes your brain not like bleed. So, but this is a yield stress. It's in PSI. So that many PSI is what it can take. And so PSI is force pounds per inches squared. So we can just rearrange this equation for that force. And you can say force max. Sometimes that's easier. Force max is breaking, or is the max strength times the area. But the terminology is force yield is yield stress times the area. So we can do that for this bar 1. You know what I mean? So we can go pi over 4 and then d1 squared, and we can chisel out a number for the yield force for 1. We can do the same thing for this yield force for 2. It's compressive, but same thing. This is steel, because you can just tell. You probably can't. No, I'm just joking. But anyway, once you get used to this, 200 megapascals. This is 250. Is synonymous with steel. And all right, so for this one, the force max is going to be the yield, the strength times area, pi divided by 4 d1 squared. Cool. And at the end of the day, that might give us P. It'll get us pretty close. So we're going to throw this into our calculator. 250 times 10 to the 6. Stored that as alpha O. Cool. And then we're going to do alpha. Well, so there you go. So we're going to go alpha O, alpha pi divided by 4. We didn't do pi. There we go. And then times the diameter. That's going to be 0.2. 0.2. We got to divide by 1,000. No, I'm sorry. This is 20 divided by 1,000. That's going to be in meters. So, and then square it. And then, whoa, we did something real bad. We threw a Q in there. We wanted to store this as alpha O. All right, hell yeah. So we get 78,539. So that's the force that this can elongate. That'd be the P max if you just had that. So now we're going to go P max on this, and we're going to go alpha. Same thing. We just bring it up, but our diameter is a little bit bigger. It's 25. And we get 122,718. So now, if you wanted to solve the problem real fast, you just add these together, but why? You know what I mean? No one knows. But that's why I think this problem should have strain in here, because then you could mentally figure it out just a little bit easier. Because let's say these are springs, and when we do reach the max force, we're going to have a max change in length of that one. And then when we do pull this one, we're going to have a max change in length of this one. So the plastic load is going to happen when this bar changes in length to there. You know what I mean? So we can actually do this, and even though it doesn't give us, we're gonna throw, see this equation? We're gonna throw F divided by A right there, and then change in length over length. And the reason, and if you do that, we're gonna make a fast video. You get this equation. Change in length is FL over EA. We've been doing this a lot. And so this says that, hey, what's the change in length of this one? Well, it's this force max of the first one. So I mean, this bar alone can only stretch that length, and we can find that length. And we're going to say that length is, if it just looks like this, that length is basically this force times L over 2. So we're going to have Fy1 L over 2 divided by E times the area of this, which is pi over 4 d1 squared. Cool, and we can throw that into our calculator. So I'm going to store this as F, and I'm going to store this as G. And let's get some more time on the clock. Alright, hell yeah, we're cruising and we're crushing. So you want to find this change in length, so this is going to be stored as F, and L, the length of these two things, it doesn't even give you it. You know, it just says just in general. So it's just going to be a function of L. And so we're going to have F divided by 2, alpha F divided by 2, divided by alpha E. So it doesn't even give you E either. You know what I mean? So that's a bummer. But now we can, so essentially this is the strain. You know what I mean? So we can back up. We can just see that this is the yield stress. Yield stress times L over 2 divided by E. So it's yield stress L divided by 2E. That is the change in length for that member. So I think this might make the problem harder. But just visually you can see what's going on. This thing's going to hit its plastic load when the other, yeah, you know, you do need a continuity. I think you do. I think you do need to do it this way. I just wish they gave you the modulus of elasticity and the length, because then you could just solve for it. But we're just going to have to use these as variables just for the time being. So now what we're going to say is when this one changes in length by this much, then that's when this one's going to hit its plastic load. And essentially, if you just pulled on this one, you're going to pull 78,000 pounds. But when you do this, this spring, this acting like a spring compresses and is pushing back. So then, because it's pushing back, you have to this applied force is going to be definitely greater than 48,000, and it's going to be well, I think it's just adding these two up. Let's see. Oh, yeah, holy Toledo. And that is true, because it's a fundamental of plastic. Even though that this one is going to go plastic maybe, well, no, the plastic load is going to happen at the same change in length. I think if these materials are made out of the same material, you know, if you have a length of material, you can only change its length by so much. That's this strain. It says change in length over this length. You know what I mean? So you have two identical lengths, and that means that you can increase this one by a change in length, and you can decrease this one by a change in length. And when you do that, you have reached the max stress in this bar, and you have reached the max tensile stress. You've reached the max compression and max tensile stress in those bars. I'm just trying to figure out, you know, what's the best way to relate it. It's really easy if you have a value of E and strain, because then you can actually just kind of calculate this length, and we do. Here is the calculated length for that, and that gives us the change in length. Cool, so now we're going to say that, yeah, and then both the change in lengths are identical. So that really, this equation, I guess this equation is synonymous with this equation. So holy Toledo. So basically it's just the max force, And is it true that even if these lengths weren't the same, the plastic load would probably be the same? I don't think it. I'm just gonna go out on a limb, and I'm gonna say it really doesn't matter. If this thing will look like that, and you applied the load here, because when it comes to plastic loads, what we say is that, hey, once you reach this, to this poundage, it can no longer, provide any extra strength. You know what I mean? If you apply a small load, it'll have a small force in this member, and this member can only take up to 78,000. The second you get to 100,000, this member is only pulling back in this direction 78,539. So that's when you pull on it like a spring, it's wanting to pull back, and then when you're pushing on this one, to push on this one, you have to pull this one. So and to make them both go plastic, you have to put a force on this one to reach that value, and then you have to put a compressive force on this one to reach that value. At that point, then this force is, if it's greater than that, is just going to move this whole thing like Play-Doh. But right at that limit, it's going to hold, and it's just the additive value of those two numbers. So it's F plus alpha G. It's 201.258, and they do this as 200, and this is in newtons, so it's 201 kilonewtons. So I don't know, you know what I mean? At the end of the day, I tried my best. That wasn't a very good, explanation. I would love to have modulus of elasticity and strain, because then you could calculate that change in length. There's just something satisfying about calculating that change in length and showing that it's identical to this change in length. And then you can calculate the force in either of these members due to the force of a spring is K change in length, and K is EA divided by L. But they don't give you numbers for L, they don't give you numbers for E, so you're just left with this equation. But I think that's the take-home point at the end of the day. Material mechanics can be nice because you have two equations that kind of can get you there at the same time. You know what I mean? Two checks on reality, because these two equations are we've talked about that a lot, but how they're just kind of, they're related by, you know what I mean? Even though this number is huge, like for steel 58,000, and how is that number equal to 0.002? Well, it's because you have a proportionality constant, and that's E, and that's a massive number. Massive number times a tiny number gets you to that 58,000. All right, we're trying to make shorter videos, trying to explain concepts, and I think we did an okay job. So there you go. Thanks for joining me, and that's a video.